Good morning, class. I suggest we wait a minute. Um, it seems like there's only 30% of the class in attendance right now, so I'm going to give it till maybe a minute past the starting time before going ahead with the lecture. All right, more people joining in, but I'll start anyway in the interest of time. This is welcome to December. Welcome to the last week of lecture for the semester. Um, just a few more things left to do. Reminders for you. There is homework 6 that's due Thursday. That's the day after tomorrow. It involves implementing a bunch of classifiers and working on the same data set that we saw for homework 2. And there's also a final project that's due on December 11th. That is next Friday. And this involves submissions to both Kaggle and Canvas. So there will be 3 more submissions on Kaggle and a report on Canvas and your code. I'll be posting an announcement about what your submission format should be and all that. Just a reminder, there's a bonus for students who are in the top 10 in the leaderboard on the private leaderboard. This is you get half a letter point bump up, as I had mentioned, I think sometime back. Are there any questions about the homework or the project? And so there's a question about, is there a review of what kind of concepts we should expect on the exam? I'll post a review document to kind of just help you think about things or plan things. I'll post it most likely before Thursday's class. There's not going to be a practice final simply because the format for this final is so different that I'm trying to get things together. The argument against a practice final for when the format changes is that basically a practice final is full of questions that will not show up in the final. In terms of format, it will be something that looks like your homework, one of these Canvas quiz homeworks. So you'll have to, it'll be multiple choices, like in homework 3, for instance, or some things where you fill in answers and so on. So it'll be a similar format, except with a time constraint, and you get only one shot at it. But hopefully that should, and hopefully the review that I'll post will help you prepare for the exam. Are you anticipating the final taking the full 2 hours? Depends. I don't think it should take the full 2 hours, but it might. Historically, the final exam does not take 2 hours, but then that's also an in-person on-paper exam. So I don't expect the final exam to take the full 2 hours, but I do want you to block out the full 2 hours just in case you need it. Would it cover material from the beginning of the semester? Actually, everyone's talking about the final, so let me also bring up a slide about the final. Yes, it covers everything that we've seen in the semester. It's going to be available for the entire day of December 8th. That's next Tuesday. But you get to pick which 2 hours you want. And of course, the Canvas thing will shut down at midnight. So you make sure that your 2 hours doesn't start at 11 o'clock if you want to go for 2 hours, 11 p.m. I mean. We will be available on Zoom if you have any questions for specific blocks of 2 hours. I'm aiming for 3 to 4 blocks where either I or the TAs are available. But again, there will be an announcement about when we will be available so that you can plan things out. Do we know what kinds of problems will be on the exam? Will it be multiple choice? Yes. It'll be mostly multiple choice, numerical calculations, and some sort of short answer questions or groups of short answer questions that are thematically connected. So there's a question about, so I think I missed a question about the project. Can we submit multiple predictions on Kaggle and check if the accuracy is improved? You can choose the 6 best submissions. There's a couple of things I wanted to mention about that. So the first one is you choose your 6 submissions that you want to publish, and you don't have the 6th or best submission scores are not the ones that are going to get chosen. Anthony, that's not quite right, because that's what Kaggle does. But for the purpose of this class, if you, for example, submit the same run 6 times, it counts as 6 different submissions, and they would all be if they are your best, they'll all be the best. So that's not how it works. What I want to do is what I would like you to do is tie your Kaggle submissions with your report. So in your report, I would like you to help me understand which 6 submissions you would like to be treated as the chosen ones. So and that will allow me to also make sure that you have covered the span in terms of the different algorithms and all the different rules. So you can. The other point I wanted to mention was you can submit multiple predictions and see if the accuracy is improved. However, keep in mind that there is a restriction of I think maybe 2 or 4 submissions per day. So you have to be careful with that. I mean, you don't want to you want to give yourself enough room so that you can actually submit. Try not to overfit try not to overfit to the Kaggle leaderboard by submitting something, looking at the accuracy there, and then using that as feedback. To improve your algorithm. All right. Few other questions. What do I need to identify the Kaggle submissions? They don't give an ID or anything. Yes, and this is kind of unfortunate. What I would like is any way in which I can understand which submission you're talking about. So Kaggle allows you to write comments, for instance. If you have written comments, you can use those to identify. Worst case, you can say, I can, in my view, I can look at a timestamped version view of your submissions. So you can say, I want the submission I made on such and such date, or you can count from the bottom or from the top or something like that. So just any way in which your submissions are unambiguously identified is okay for me. It's unfortunate they don't give an ID. In an earlier version, I think they used to have an ID that was visible to you. I still can see an ID, but I didn't realize that you can't see it. But any way in which I can understand which submission you're talking about is fine. Off topic, I've seen this concept of bias variance trade-off floating around. Can you briefly touch upon what it is and how it fits into the context? That's a great point. So I will be talking about bias and variance on Thursday, just before wrapping up. So this is very briefly, bias and variance. Bias is like asking, is your learner biased towards a certain hypothesis? And high bias could mean that your learner, even without looking at the data, has a preference for certain hypotheses. So maybe that's a good thing, maybe that's not. Variance is about how much does the performance of your classifier change based on the data set that you choose. So how much variance is there? And it turns out there's actually a trade-off between these, and we'll talk about that on Thursday. Question on homework 6. I'm still confused about the implementation of early stop for training. I'm trying to track the loss at each epoch, but the value is big. And fluctuates a lot, so I cannot see how to define the criterion. Any suggestion? Actually, it should not fluctuate a lot. So let me just briefly talk about that. One thing that you should normally see is if you plot the epoch versus loss, roughly speaking, you should see a drop. There will be some little fluctuation, especially with because we are dealing with a stochastic gradient descent, but there should be a drop. So this is a good thing. This is not, because we are minimizing the function. This is not either. So usually if you see something like that, that might suggest that there's a bug. The other point to mention is be careful on how you compute the loss at the end of each epoch, because this is a common bug that I have noticed. So you can have, let's say that you have, roughly speaking, most of these algorithms that you're implementing look like for, let me create some space for myself. So most of these algorithms have for epoch in something, and then now you do for you have your parameters. I'm going to call them W example. I'm assuming there's some shuffling, and then there's an update. A mistake that people can do is have a initialize loss equals 0 here and loss equals loss plus example. Something like this. This is a problem because losses, the weights keep changing, and you can't accumulate the loss within this loop. What you need to do is accumulate the loss in a different loop where you have for in T. So this is a mistake that people, I mean, this is the right way to do that. So just make sure that you're not making that mistake. If your loss fluctuates too much, there is another thing that might be happening is that your learning rate is too large, and as a result, you're just bouncing around the loss landscape. That's something else to look at. Okay, so is it okay if the plot is plotting accuracy rather than the loss? I've just realized that's how I've been doing it. So technically speaking, the accuracy and the loss are different. The accuracy is, in some sense, asking for a decision, or rather, accuracy is really measuring the 0-1 loss. Or so error is the 0-1 loss. Accuracy is 1 minus error. So accuracy is connected to the 0-1 loss. The thing that you should remember is we are never optimizing the 0-1 loss in any of these algorithms. We are hoping that the 0-1 loss goes down by optimizing maybe the SVM loss or the logistic regression loss or the log loss, for example. These two things are different. In general, plotting accuracy is also a valid thing, where you plot the accuracy on the training set, you can plot the accuracy on the dev set, and what you might notice is that the curve might look something like this. Accuracy on the training set keeps going up, the accuracy on the validation set or the development set goes up and then comes down, and this is a good point to stop. And this is, while this is perfectly reasonable, I would recommend, just so that the grading becomes easier, I would recommend that you plot the loss, simply because it just makes, while the TAs are grading, it just doesn't seem jarring, and you accidentally get docked points, and then we have to kind of go through the review again. Another last couple of questions before we move on to the lecture. At each epoch, we shuffle the data set and iterate over each example once. Is this the case for both SVM and logistic regression? Yes, because in both of these, we are we are implementing a stochastic gradient descent, and that step is the only thing that changes. Everything else is going to be the same. I mean, of course, I have skipped out on a lot of details here, but I hope you know what I'm talking about. I remember you mentioned about early stopping criteria in the last lecture. Instead of having a fixed number of epochs for cross-validation and training, can you explain about that? So there are a few different, okay, so let's just quickly revisit this point. One of the questions to think about is, when do we stop? How many epochs should learning run? And there are multiple ways to do this. One of them is just a fixed number of epochs. So let me just make a list here. Which is easy. You just have a number and you decide to stop after those many epochs. Another one is, let's call it loss change. When the loss change is less than some epsilon, what you do is at every epoch, you measure the loss. So let's say that I'm going to show it in a plot here. At every epoch, you measure the loss. And I'm going to show a smooth curve, but it's invariably never this smooth. So let's say that you get a curve that goes down like this. Now, if you zoom in here a bit, what you'll see is it seems like, let's say this is an epoch, this is an epoch. Let's say these are your epochs. Now, we can measure what's the change in loss between any two epochs. So let's say this is epoch 1, 2, 3. So I can ask, what's the difference between the loss in these two epochs, and similarly these two epochs, and so on. And you can decide if the change is less than some fixed number epsilon, then you decide to stop. You declare that learning is converged. So this is a convergence criterion. Another possibility is you can say that the loss, validation accuracy change, the validation accuracy starts dropping. And here what you do is you keep track of you have two data sets. You have the training set, of course, and then you have validation, which is not used for training, remember. So you keep track of the validation accuracy for each epoch. And usually what you see is it goes up, and then after a point it plateaus or even goes down. So you can choose either, somewhere around here is when you decide to stop training. And all of these are perfectly reasonable things. There are a few other approaches where you can keep track of relative changes rather than the absolute changes and so on. But these are the most common things that are used. I hope that clarifies things. Oh, one other thing is for cross-validation, for your homework, you can choose to either use these strategies or just use a fixed epoch. And this, I think, touches upon your next question. This is after all the hyperparameters are found for cross-validation. Just for the sake of simplicity, you can just use the fixed epoch strategy, fixed number of epochs, because it's just going to be easier and it's often good enough. So you do all of this when you're training and not during cross-validation. When we are plotting, this is Ben's question, when we are plotting the loss function, does this include the regularizer? Yes, because the function that you're optimizing is regularizer plus, so if you think of it as some function f of the weights, that is regularizer of the weights plus total loss. And this is the function that is getting minimized. And usually when we say loss, we mean this regularized loss. And you need to measure, because that's the function that we are minimizing, and that's the function that we expect will go down. And maybe this is also the answer to Louise's question from before. You should be plotting regularizer plus the total loss, not just empirical loss, because we are operating with all of this falls under the umbrella of empirical regularized. Oh, actually, it's the other way around. Sometimes you also see this as empirical risk minimization, because this is the function, this is the regime in which all of these things are operating. The function to consider is the regularized loss. I hope that answers the most of your questions. We're going to start with today's lecture if there aren't any other questions. For the third option, you need to split that part of the data set as validation, which is why maybe you should not be doing that for the homework. That's why I asked you to do this thing for the second option. The bias variance trade-off is coming on Thursday. All right. Today, the plan is to talk about a couple of topics that got skipped along the way, and I would like to kind of tie them up. The first one is just this idea of generative and discriminative learning. This is something that we haven't really touched upon through the semester, but it's an important concept that you should know about. So what we saw for pretty much all the semester was we are given there's some fixed and unknown distribution of examples, and there is a function. This is not right. So there's a fixed and unknown distribution over the examples, and we have some hidden function, and you can play this in a few different ways. But in any case, we are given a data set consisting of labeled examples, xi, yi, and the goal is to identify a hypothesis space that by using this empirical loss minimization. So we minimize average loss over the training data. And the guarantee that usually comes with this is if we find an algorithm that, if we find a classifier, that minimizes the loss on the observed data, then we'll usually, the guarantee takes the form of some generalization statement. So the learning theory, for example, will tell us that you get good future behavior. All of this, all the models that we have encountered so far are come under the umbrella of something called discriminative models. Discriminative models essentially learn how to make predictions. You look at many labeled examples, positive and negative, or for regression examples labeled with real numbers, we discover regularities in the data with respect to how the labels are produced, and use this to construct a prediction policy. And there are ways to introduce assumptions into the system. One way or another, when we are approximating this function that maps x to y, we are estimating the conditional probability of y given x. Even though we are not explicitly doing it, we are essentially we are asking, given an x, how do I make a prediction? Now you might be wondering, okay, so this seems like everything that we've done, so what else could there be? Importantly, notice, we do not care about how the x is distributed. We don't care about whether x, the instances have some regularity in them independent of the label. A completely different style of building models involves what is called a generative model. A generative model models how instances in each type, in each category are generated by modeling the joint distribution of x and y. So that is generative models model p of x comma y, p of y comma x. But by Bayes' rule, we know that p of x comma y is p of y times p of x given y. And usually generative models, oh, not equal to, but proportional to. Oh no, this is equal. So usually generative models learn two different statistical functions. One of them that says what's the prior probability of label, and the second one that says what's the likelihood of generating this example given a label, and that gives you the p of x comma y. So you learn two functions, p of y and p of x comma y. And then when we need to make a prediction, we use Bayes' rule to construct p of y given x using these two. So p of y given x is proportional to p of y times p of x given y, and you can use this to make the prediction. The classic example of a generative model is a naive Bayes classifier, which unfortunately this semester we had to skip. But if you're interested in knowing about it, you can find the lectures from the last year and go over it. Naive Bayes is a rather simple classifier, and it's like the standard example of a generative model. The important difference is a generative model uses the model capacity. When I say model capacity, I'm figuratively, I'm talking about this figurative capacity that the parameters of a model gives it, the capacity to learn or the capacity to represent patterns. So a generative model uses the capacity of a model to generate both how an example is exists and how it's associated with the label. So in other words, it's a joint distribution of x comma y. The standard examples of generative models are the naive Bayes classifier, the hidden Markov model. Another famous example is the topic model the family of models that are called topic models. All of these are generative models. We haven't covered any of these, unfortunately, but if you're interested in this, I can suggest a few classes where there's some time that goes into these things. In contrast, a discriminative model learns instead of p of x comma y, it uses p of it learns only p of y given x. In other words, instead of talking about how examples are generated, it uses the model capacity only for characterizing the decision boundary. The standard examples of discriminative models are logistic regression, support vector machines, all the neural networks that we saw, conditional models, any model that where we cannot, at the end of learning, we have no way of knowing what is p of x, either by itself or p of x given y. If we cannot compute this, either of these things, we have a discriminative model at hand. In both cases, of course, notice that there's a separation between inputs and outputs. So there is some x, there's some y. In generative models, even though there's a separation between inputs and outputs, the job of modeling involves treating them as the same thing. So you just learn a single joint distribution. There's a question: what generative models are used in the industry? Is naive Bayes used much in industry? I would say that the naive Bayes is actually a very useful thing to know. If nothing, it gives a fantastic baseline. And in addition, generative models lend themselves to useful further ideas, like if you have unlabeled data, we can, in some sense, hallucinate a label for that thing by using a generative model, because we can ask, the math works out. So I don't know if naive Bayes is used too much in the industry. I suspect it should be, given how simple it is and how surprisingly effective it could be. In fact, there are a few papers which talk about this exact question: why is naive Bayes as effective as it is, given that it's such a simple thing? And it tends to be useful for those things. And also another place where it is useful is because, remember, a naive Bayes and all generative models end up learning p of y and p of x given y. You have these two distributions. And now when learning is done, suppose, for example, what this means is I can ask y could be label, so spam or not, and x given y is email given spam, for example, or email given not spam. So there are two distributions there. Now, with a generative model, using this distribution, I can say, okay, now sample a spam email for me. So create a spam email for me, or create a not an email that is not spam, and it can that can be a very useful thing, because now you can create these examples that look like they have come from this distribution. Interestingly, I have never seen a sampled text document ever look anything reasonable, but that's just because of the poverty of our modeling assumptions. Now, a couple of questions, it seems. Is there a mapping that can be done between generative and discriminative models? For example, does perceptron have a corollary generative model? That's an excellent question. I don't know if perceptron has a corollary generative model, but logistic regression definitely does. So naive Bayes and logistic regression form what might be called a generative discriminative pair. What that means is, if given that a generative model learns these distributions, right? Which means using this, I can compute the posterior P of y given x is proportional to P of y and P of x given y. So with naive Bayes, if you do this, go through this process, you'll see that for example, with some assumptions about what x, the P of x given y looks like, what you will see is that the posterior distribution, the P of y given x, ends up taking the form of 1 over 1 plus e power minus I w transpose x for for a specific definition of w. Effectively, what this means is both the naive Bayes classifier and the logistic regression classifier define the decision boundary using the same functional form, except they come at it in different ways. The logistic regression directly learns this w here, and naive Bayes does not ever learn the w. Instead, it learns these two functions that put together give you that thing. So there is a neat mapping between generative and discriminative models. The hidden Markov models, discriminative pair is called a conditional random field, and so on. So this is it's a well understood thing. There's an anecdotal use case of naive Bayes. I recently used naive Bayes to predict whether or not voice transcription files were in Spanish for my corporation. Anecdotal, but naive Bayes predicted better than SVM and logistic regression. I would probably contest that, because usually I have found that naive Bayes, it depends on your hyperparameter tuning. Usually, the logistic regression and SVM style models end up performing better if all you care about is the prediction quality. If there are other criteria that you care about, then maybe these classifiers don't do better. And the reason is, in discriminative models, you're optimizing exactly what you want to solve, namely better prediction quality. So let me give you an example of this. So imagine that you have a data set that looks like this. There are red circles and blue circles, and there's a separating line between them, or a separating curve. A generative model characterizes both the inputs and the decision boundary. So it uses the model capacity to say that there's a cluster here, there's a cluster here, there's this cluster here, this thing here, there are all these points. So it tells you how the data is laid out, and also how the separating boundary works between them. In contrast, a discriminative model does not care about the fact that there are all these clusters of points around. It uses the model capacity to only talk about this decision boundary and nothing else. So in some sense, a discriminative model does less work. Using assuming that all things are equal, using the same number of parameters, it has to do less work, And as a result, it tends to be slightly easier to learn. So we should probably take this question offline about whether the naive Bayes is outperforming SVM and logistic regression. If that's truly the case, I would be very curious. I'd be very interested in knowing more about this application, because that's something that I haven't encountered much, and I would love to learn. So it seems like generative models need more memory than discriminative models. Well, that's not quite the case, simply because you're giving it the same number of parameters. It's asking more. I can see why you say that, or I can see why you ask that, because the generative model is doing more or attempting to do more with the same number of parameters. That's probably a safer way of putting it. It's trying to say, okay, not only is it, for example, in if you want to think of spam and not spam classification, a generative model has to learn P of email given spam, P of email given not spam. And this distribution, if it is perfectly characterized, it has to, in some sense, write every valid email that was ever written. And this one has to write every spam email that was ever written using the same number of parameters. And of course, it's going to be impoverished. So I can see your argument for more memory, but it doesn't quite translate to memories as much as the right metaphor to use would be more capacity. The discriminative models use the capacity of the model to directly characterize the decision function. And if that's all you care about, then you're better off using a discriminative model. On the other hand, if you actually want to characterize the joint distribution, then you have to work with a discriminative model, a generative model, sorry. I said that neural networks that we learned so far are discriminative models. Are there generative neural networks? There are. They are called generative. So yes, they are generative networks, which they're kind of really cool devices. What they do is you have. I'm going to draw a cartoon example of one. So what you would get is, I'm going to put a black box and call it a neural network. Internally, it can be anything. And imagine that I have a neural network that generates an email. What does it take? What input does it take? So this is the output. What input does it take? The input is a random, any random input. So given a random point, it generates an email. So essentially, this is like saying this object here that's on the screen is something that samples an email out of randomness. And implicitly, it is creating emails from, it could also be like a conditional generator. It could be a label, for example, a label and some source of randomness. And implicitly, what it's doing is, given a label, that we can't control. Given a label, you're producing an email, so it behaves like we are doing P of X given Y. And this, the place where generative neural networks tend to show up is in the context of something called GAN, generative adversarial network, where you have a generator of an email attached to another system that takes an email and produces a, let's call this NN2, that produces a label. And then you have this very cool thing where this is called the discriminator, and this is the generator. And you set up a loss function where the discriminator and the generator fight against each other. And the goal is to get a good generator. That's how generators are trained. So this is I would call it an advanced topic. So we won't talk about that in much detail, but it's a fun thing to explore if you're interested. So the important thing here is a generative model tries to characterize the distribution of the inputs. A discriminative model does not care. A discriminative model only wants to characterize the decision boundary. Are there any questions about discriminative and generative models? Any other questions? So far, we've had a lot of good questions. How come we've only seemed to have covered discriminative models? That's a fantastic question. Um, there are a few reasons. One of them is most of the time when we are using machine learning, we are using any kind of an applied setting, we end up using it to make predictions about objects that are there. So we are given an email and I want a label. We are rarely in the position where we have to create an email given the label. And as a result, the generative discriminative models tend to be more useful. The other reason is most of the successes of machine learning that we have seen, nearly all that you might hear about in the media, tend to be discriminative models simply because we are invariably trying to solve a particular task. And as a result, discriminative models tend to be more um, widely seen, more widely used, and the math for it is quite extensively developed. Doesn't mean that generative models are not well developed. In fact, one strong success, like naive Bayes is such a ubiquitous thing, hidden Markov models, where the standard bearer for a lot of speech recognition tasks until they got replaced by discriminative models. And then more and more sophisticated discriminative models like neural networks. And topic models are still widely used, and they're all generative models. So it's not that they're not used so much, but discriminative models are way more widely used. I do agree that generative models are cool, and maybe that's what the December break could be about. What about AI? Do you mean artificial intelligence? There's no one thing called AI, right? I mean, it's just this piecemeal thing. You can use it to you can use what works to build uh, uh, what you want, and it depends on the application. So if you, for example, want a system that generates a book, for example, um, then you might want to think about generative models. However, to kind of talk about this question that Anthony raises, there's a model that learned how to write a book like Harry Potter, that's used as an example in deep learning. Is that a generative model? Actually, not quite. In fact, there, the output space Y is the book. So it's building up model. It's building up the output using a collection of discriminative models. So that's the other reason why discriminative models are popular, because you get to define what X and Y are, and you can just use what you want to be Y. So uh, pretty much all these examples that you might have heard about that use recurrent neural networks and things like that are discriminative models. All right, I'm going to switch topics now. In maybe the 35 minutes that are left, I'm going to talk about another important topic that we didn't get to cover, namely the nearest neighbors classification. This might be the easiest classifier that we will see. So it's one of these things that is worth spending some time on. This lecture, we'll talk about K-nearest neighbors, the basic algorithm. We'll talk about the hypothesis space that the nearest neighbor classification talks about. And if time permits, I will try to confuse you by talking about the curse of dimensionality. So let's talk about K-nearest neighbors first. First question, imagine that you're given a collection of points and you have to label them. Some of them are colored blue and some of them are colored red, and you're given three unlabeled points. If all you have to do is, hold on, Anthony, there's a quiz, there's a poll that's out there. If all you have to do is label the points using their nearest neighbors, how would you label them? And you should be able to see a poll. Oh, yeah, the answers are on the slide as well. So clearly Okay, so there, I guess that I skipped a little too far ahead. Oh well. But it seems like there seems to be some disagreement between on the label for point B. I would have still called it red because it's closer, but that's fine. But I hope you get the idea. This is pretty much the most. This is pretty much um, the point of nearest neighbors. But instead of effectively, what we do is we are given a training set, and in feature space they are positioned some wherever they are, and the points have different labels. Just by virtue of the fact that some probe point, let's pick this point here, let me not use the color, some probe point is maybe closer to one type of a point than another, we are implicitly or by the by looking at one of these nearest neighbors, you are implicitly coloring the entire space. So you are partitioning the entire space using the label of the nearest neighbor. This is pretty much the entire the main point of nearest neighbors classification. By virtue of the fact that the points are in the space and have some colors, even though this entire region does not have any point in it, it's closer to the blue points than to any red points. So we assume a reasonable assumption is to say that the circle that I just drew is also colored blue, and in fact the entire region. This depends on how many nearest neighbors we look at, of course. The basic version of the nearest neighbors algorithm is rather simple. As always, we are given examples, xi, these are feature vectors, associated with some label yi. This might be the easiest learning algorithm you will ever see. Learning literally involves reading the examples and storing them in some place, maybe storing them in a database. All the heavy work happens when you have to make a prediction. When a new example X comes in, you iterate over the entire training set and find the training example that is closest to this example. And then you predict the label of, you say that because this example is closest to xi, you say the label should be yi, whatever the label of xi was. That's pretty much the entire point here. KNearest Neighbors, as Ben points out, is a slight extension to this. Instead of looking at the one closest example, you look at the k closest training examples. And then you use these to construct a label. So how do you do this? So maybe, let's say you have a classification task. K is a hyperparameter. And in fact, it's a fun exercise to think about what happens when k goes to infinity or k goes to the size of the training set. But what do you do with if you have how do you construct the label using these k training points? So what we have is we have some examples. Let's use pluses. Let's say this is the data that we have, and let's say this is the new point. And how do we know what should the label for this new point be? Should it be plus or minus? And why? This is a suggestion. You either weight them uniformly or by some distance metric. Implicitly, what you're suggesting is we can aggregate all these labels and see that there's like some sort of a voting mechanism here. So this easiest way to aggregate the k labels that we get is to say that every neighbor votes on a label and you predict the most frequent label among the neighbors. You can do some sort of weighting by saying that neighbors that are farther away get smaller votes. What do you do for regression? Instead of pluses and minuses, what if you had some numbers in the neighbors? Any ideas? You can use some metric like 1 over d square, but what's the simplest thing you could do? You can literally, like, you can just take the average. You're given a few numbers, and you need to find, there's you're told that the test point is close to that. A reasonable thing to do would be to take the average. You could kind of make it more sophisticated by saying farther away neighbors contribute less to the average by using a weighting scheme. So the easiest thing is just the unweighted mean. You could be more sophisticated about it. This is the basis of K-nearest neighbors. I mean, it's entirely, in some sense, if this is all, if at this point you're ready to implement your own K-nearest neighbors classifier, this class of learning algorithms are called instance-based learning, where the learning process stores examples in some data store, and prediction involves classifying the labels using similar stored examples. Sometimes it's also called lazy learning, because most of the computation is performed at prediction time, because you're not doing anything at training time. All you're doing is putting it in a database. It does feel like rote learning, but surprisingly, there's some amount of generalization when you change the value of k. Because if k equals 1, you go for the nearest neighbor. But if k is 2, you are willing to kind of overrule some neighbors. So there is a little bit of generalization, or equivalently some sort of smoothing that happens when k becomes larger. Are there any questions about this? In fact, what I would like you to think about is, imagine yourself implementing k-nearest neighbors. What would be a problematic thing here? What do you need to do? Outliers are always a problem, but what is something uniquely obnoxious with k-nearest neighbors? How do you break ties with even number of neighbors? I would suggest just don't even get yourself into that situation. Use an odd number for k. There's like, you get to pick k, right? So why not just try odd k rather than even? Outliers are definitely an issue, and you will get, especially with one nearest neighbors, you might end up with scenarios that look something like this. So you could have, let's say, you have let me use pluses and minuses. You have a plus here, you have a plus here. And then you have some minuses in. Now let's say a minus sneaks in here. Very clearly, let's call that point x. Very clearly, that point is not in the right neighborhood, so to speak. So if a new point comes in here, it's probably better to call it a plus than a minus. But if you use one nearest neighbors, it will be a minus. If you use maybe 5 nearest neighbors or even 3 nearest neighbors, it'll end up becoming a plus. So you can deal with this by increasing the value of k. If k is 1, you will definitely overfit, because what you will do is there will be this tiny region around this point which will be labeled as negative. So it does overfit a bit. Let me move on, because there are a couple of technical issues that need to be dealt with. The first one is, what do we mean by distance? How do we define distances between instances? Usually when we think distances, we think Euclidean distance, but does not always work. For example, what if you have features like in one of the first examples that we saw in the semester with the tennis game? What if your features are outlook, and it can take either, I forget what the 3 values are, but it took 3 different discrete values. What does a distance mean in this case? This is a good place where we can inject some sort of domain knowledge. So if you have, for example, feature values that are closer to each other than others, then so let me instead of this, let's say that we have a restaurant rating, and this feature can take maybe 1 star, 2, 3. Let's say this feature can take 5 values. A reasonable thing to do would be to say that this value is closer to this than to this, so that the distance between 1 and 2 is maybe 1 unit. So you can treat it as a number, even though it's just some abstract object called stars. Similarly, if you have something like if your features are overcast, sunny, and rainy, these two features are far from each other, but this and this are closer to each other. So you can introduce some knowledge that you know about the feature space in your definition of the distance. If you have numeric features represented as n-dimensional vectors, you could, of course, use the Euclidean distance, the L2 distance. It's the standard distance formula that we've seen since high school or something. And this works. This is often a reasonably good starting point. You could use the Manhattan distance, also called the L1 distance, which is simply you take, so in Euclidean distance, what you have is you take the difference of each dimension, you square it, add the squares, and take the square root. In the L1 distance, you just take the difference of each dimension, take the absolute value, and add up the absolute value. So it's the absolute lengths, absolute values of, it's the sum of absolute values of all the differences. All of these, both of these are special cases of something called LP based on these LP norms. Euclidean is based on what's called the L2 norm. By the way, L2 is something we've already seen before. Even for regularization, when we use distances, we use the squared norm regularizer, and it's also called the L2 regularizer. The Manhattan distance is the L1 norm. All of these are defined in this fashion. So you take the absolute value, you take the difference of the absolute values, power p, add up the whole thing, and you take the sum power 1 over p. It should be easy to see that when p equals 2, you get exactly that. And when p equals 1, you get this thing. A fun exercise to think about is what happens when p goes to infinity. I'm not going to talk about it, but it's kind of interesting to think about. It is actually just the max, yes. So this, how do you choose which distance you should use? Most of the time, you just use Euclidean because that works reasonably well. But if you actually know something about the domain, if for some reason you believe that the Manhattan distance is a better characterizes distances between points, then you should probably use that. What about other kinds of features like symbolic features or categorical features? This is if you have a feature, for example, if you're if the feature space is about the first letter of the word. So let's say you have the word or the name. Let's say you have maps to J, and then suppose you have things like this. This is your feature. How do you measure the distance between these things? These are just what's the distance between J and M, and why should it be any more than, say, the distance between J and A, and so on. The easiest answer for this is to use what's called the Hamming distance. It's essentially the number of features that number of bits that are different. So, or the number of features that have a different value. So, for example, if you have two instances, x1 and x2, where x1 has a shaped triangle, it's a red color, the location's to the left and the orientation's up. And x2 has a shaped triangle, but the color is blue, location's still left and the orientation's down. There are two places where this feature is different, so the Hamming distance is 2. This is a very commonly used distance for categorical features, and you can think of it as the number of changes that you need, not the number of changes, but it's the number of bits that are different. Of course, you could also learn the distance, and that makes, of course, the problem much harder. If you feel like you want to learn distances between instances, look up metric learning or manifold learning, and that will keep you occupied. But in practice, these things work surprisingly well. So let's maybe kind of very briefly summarize these things. So the advantage of the nearest neighbors is its training is super fast. It's literally adding labeled examples to a list or maybe a database. You probably should not just put them in a list because uh, then prediction will get slower. You should use something more complicated like indexing. Databases implicitly do something like that. That slows down learning a little bit, but not too much. The cool thing is that it can learn really, really complex decision boundaries. Like, look at this picture here. By doing nothing, we have managed to learn this rather complicated decision boundary uh, between the red points and the blue points. And of course, there's the other advantage in that we always have the training data. So if this doesn't work well enough for you, you can do something else with the training data. You can in pretty much all other learning schemes that we've encountered. Once learning is done, we don't look at the training data again because the classifier that we learn, the model that we learn, summarizes everything we need from the training data. We toss out the training data, but here we have to keep the training data. So that could be useful because you can do things with it. But there are a few problems with this. Nearest neighbors needs a lot of storage. I don't know if this is necessarily a problem given that storage is cheap, practically free, but it's definitely something to think about. A more pressing concern is that prediction can be slow because if you naively implement it, if you have n training examples to find the label, let's say even for one nearest neighbors, you need to iterate, or for any nearest neighbors, you need to iterat through the entire set of training examples to get the label. And you need to find the distance. If you have d dimensions, the distance grows with d, computation grows with d. So for every single prediction, you have to traverse the entire data set. So prediction can be ridiculously slow, and more data is going to make it much, much slower. So this is the trade-off. In all other classifiers that we've seen, learning might be slow, but prediction is fast. In nearest neighbors, learning is super fast, but prediction is slow. Of course, it's almost never the case that the naive implementation is used. They tend to be interesting indexing tricks that allow you to that can take the complexity from n to log n, where you kind of partition the data in interesting ways and you zoom into the region that is relevant quickly. But still, it is slower than other prediction techniques. Especially imagine that you have a million training examples. Among a million training examples, you have to you'll have to go through all of them, and that's why the order of n shows up to find the nearest neighbor. Because you can't skip any of them. Maybe it's the last example that's the nearest neighbor. So you have to go through all of them to get the label. And adding more training data is you're paying the cost of time here. So the nearest neighbors also tend to be fooled by irrelevant features. And this is an important point that if time permits, we'll get back to at the end. How does this compare to full depth decision trees? It seems like you'll get the same thing without the duplicates. That's an interesting question. So it's not quite exactly the same, because here the notion of a distance, we get to control the notion of distance, whereas in decision trees we don't have that, or at least not in the standard version that we've seen. So you probably won't get the same thing. They are kind of similar in that they similar regions of the instance space get nearby regions of the instance space get similar labels. Prediction with the decision tree is log of the size of the log of the dimensionality. The size of the data set doesn't even come into play here, whereas prediction with nearest neighbors is actually much slower. Quickly summarizing KNearest Neighbors, it may be the first machine learning algorithm, if you are willing to call this machine learning. It comes with a fascinating guarantee. If there are enough training examples, the error of the nearest neighbors classifier will converge to the error of the best possible predictor that can exist. And when I say enough examples, what I mean is if you have, as the number of examples approaches infinity, you can't do better than the nearest neighbors classifier. In practice, you should use um, an odd valued of odd case this is to address the question that came up earlier so that we break ties. How do you choose K? Well, it's a hyperparameter. You use standard methods for hyperparameter selection, use a held out set, or use cross-validation. Feature normalization is going to be important here because if you have different features that have different scales, then the larger valued features can dominate the distance. So as an example, imagine that we are trying to classify, say for some reason, we are trying to classify people into some, or maybe assign scores to people somehow, and we use features like height and weight. But let's say the weight is measured in milligrams and the height is measured in miles. I don't know why you would do that, but let's say we do that. That means the height would be in really, really tiny numbers, and the weight would be in really large numbers, and which means distances would be dominated by the weight. So feature normalization can be an important thing to do when you're using nearest neighbors. There are many, many variants of nearest neighbors. Um, the common one that shows up is the one that was mentioned in the chat when we saw the nearest neighbors model. Namely, you can, instead of taking just the average of the neighbors labels, or allowing the neighbors to vote with exactly one vote, you could weight each neighbor by the distance. So neighbors that are farther away get lower influence in the label. Okay, so what we have seen now is we've seen what nearest neighbors classification is, and we've seen how to make predictions and how to train. One thing that we did not see is what is the hypothesis space, or what do the decision boundaries for nearest neighbors look like? The answer is something called the Voronoi diagram. So a question to think about is the nearest neighbors algorithm actually building a function at all? It doesn't explicitly build a function, never forms an explicit hypothesis the way we have seen so far. But we can still ask, what's the implicit function that's being computed? Because anytime a new data point comes in, the nearest neighbors classifier will return exactly one label, which means for the entire instance space, there is some function that maps the instance space to a label. So we can ask, what would this function look like? And the answer is that the nearest neighbor is really computing what's called the Voronoi diagram over the instance space. So for any point in the instance space, let's say this point here, its Voronoi cell is a polyhedron that consists of all the points in this space that are closer to it than any other point. So if you have, it might look something like this. The claim is that all points in this region are closer to the point in the center than any other point. All these points, this is a well-defined set. All points inside the set constitute what's called the Voronoi cell of this point. The Voronoi diagram is simply the union of the Voronoi cells of all the training points. The reason I'm bringing, so it might look something like this. So you partition the entire instance space into regions. So if this point is A, all points inside the cell are closer to A than any other point here. The Voronoi diagram covers the entire instance space. So now if we assign labels to these points, so some of these points are blue, some of these points are red, the Voronoi cell is simply consisting of all points that are closer to this blue point than anything else, which means if you apply one nearest neighbors, every point inside this particular Voronoi cell, every point inside this Voronoi cell will be closer to the point at the center than anything else, which means all those points will get the blue label. So effectively, the entire region, every Voronoi cell gets a certain color, and that's the and the boundaries between these Voronoi cells of different colors constitute the decision boundary of this particular one nearest neighbors classifier. This picture uses Euclidean distance with one nearest neighbors. If you change the distance, the Voronoi diagram changes. If you go from one nearest neighbors to k nearest neighbors, things get much more complicated. I will leave it as an exercise for you to think about. It also partitions the space, but the decision boundary gets much more complicated. In some sense, there's some smoothing going on. There's a question, okay, what about points on the decision boundary? What label will they get? The answer is, well, doesn't really matter. You toss a coin. Are there any questions about Voronoi cells? Voronoi cells show up quite a bit in things like robotics, in areas like robotics. So those of you who are in the robotics track might have seen this or will see this at some point. Sort of a simple exercise for you to think about is, if you have only 2 training points, what would its Voronoi, what would the decision boundary be? Let's say you have 2 training points and we want to build a one nearest neighbor classifier. What would the decision boundary be? Does anyone want to take a guess? What you get from an SVM? What do you get from an SVM? Okay, a line, but more precisely, you get a line that bisects these 2 points. Because effectively, this is any point here, you can ask, is it closer to this or to this? And if as that point gets closer to the thing, you get this bisecting line. What is MLE? Most maximum likelihood estimation, I assume. Or is there something else? While you type, this is just a useful exercise. Now you can think about what happens when there are 3 points and kind of build up on that. All right, now we have about 8 minutes left. And I would like to talk about a problem that affects nearest neighbors, but also in general, when we are thinking about high dimensional spaces. We've been talking about high dimensional spaces quite a bit. And we haven't, it's hard to build intuitions about high dimensional spaces. And often we end up using 2 or 3 dimensions to kind of give an intuitive example. I'm going to talk about why that might be problematic using this idea called the curse of dimensionality. It tends to affect nearest neighbors a bit more than others. Simply, well, it's always there. We have to let's see what it is. So there are a few different considerations with learning algorithms. When your classifier might go wrong because of overfitting, we have spent a lot of time talking about that. Your classifier might be inadvertently meaningless because of something called the curse of dimensionality. And the idea is, the reason is that intuitions that work with low dimensional spaces in 2 or 3 dimensions don't really always apply to high dimensional spaces. Let's see what happens. Suppose you have 1,000 dimensional features, but there are only 10 features that are relevant. We don't know which 10, but there are only 10. Anytime we measure distances between points, irrelevant features will of course hurt distances, because 990 dimensions are going to contribute to meaningless correlations between points, and it can lead to overfitting. So distances will be dominated by the large number of irrelevant features. But the thing is, even when all your features are relevant, even if all your features are relevant, we should be wary. High dimensional spaces can behave in very weird ways. So let's look at 2 examples of what's called the curse of dimensionality. So imagine that I have this square, or in general, imagine that you have a cube, and let's say that there's a sphere that's inside it, that's inscribed in it. I can ask what fraction of the cube lies outside the sphere. So we can ask this question in 2 dimensions. In 2D, a 2D cube is just a square, and the sphere inscribed in it is just this circle here. So effectively, what we're asking is, what is the area of this shaded region. We can compute that easily. So it is simply the area of the area of the shaded region is the area of the square, which is 4r square, minus the area of the circle, which is pi r square. And I can ask, since the question is asking what fraction of the points lie outside, it's the whole thing divided by 4r square. So it is 1 minus pi by 4. Nothing surprising there, nothing shocking. This is like simple math. Distances, unfortunately, don't behave the same way in high dimensions. Let's increase the dimensionality by 1. When we increase the dimensionality by 1, we are asking, given a cube and a sphere inside it, what fraction of the points lie outside the cube, outside the sphere? And if you work out the math, you'll see that it comes to 1 minus pi by 6. For a square, just to remind you, it was 1 minus pi by 4. So it has gotten closer to 1 when the dimensionality increases, because pi by 6 is less than pi by 4. In fact, as the dimensionality increases, this fraction approaches 1. As the number of dimensions becomes larger and larger, this fraction becomes more and more 100%. But this is weird. What we are saying is we're asking for the fraction of the points that lie outside the cube. And if the fraction approaches 1, that means you have a cube, you fill it up with a sphere as tightly as you can, and yet most of the points inside the cube lie outside the sphere. This, if you think about this, your head should start hurting. That's the curse of dimensionality. Most of the volume of a cube is far away from the center, which does not happen at all in 2 and 3 dimensions, but it's actually possible to prove it formally that this is almost definitely the case in high dimensions. Let's look at another example. Imagine that I have a circle, and I'm drawing another circle inside it. And let's say this gap here is epsilon. I can ask what fraction of the volume of the unit sphere or the unit circle lies in this little ring here. So in 2 dimensions, I can have a circle of radius 1, and I draw another circle of radius 1 minus epsilon, and I'm asking what fraction of the area of the circle is inside the blue region. It looks like a very thin region, right? I mean, so in particular, remember, this is epsilon. So epsilon is usually a small number. So effectively, this is a negligible space. So we can compute this thing. It is, and it's easy to show that it is 1 minus epsilon squared. And so if epsilon is really tiny, so imagine that if epsilon is 0.001, then this quantity is basically 0. So nearly nothing inside the, no part of this unit circle lies in this tiny ring. Okay, but same story. Distances don't behave the same way in high dimensions. In fact, in d dimensions, that fraction is 1 minus epsilon power d. As d goes to infinity, or as d gets larger, this expression becomes closer and closer to 1. In 2 dimensions, this ring had really no area. This quantity was nearly 0. In high dimensions, this quantity is nearly 1. Once again, in high dimensions, most of the volume of the sphere is far away from the center. What this means is we can't really trust distances in high dimensions. Most of the points in high dimensional spaces are far away from the origin, if that even makes sense. I can't visualize that in any way. It's just an algebraic fact. This is really bad news for nearest neighbors classification in high dimensions. Even if all features are relevant, in high dimensional spaces, most points are equally far away from each other. One way of thinking about this is in high dimensions, the notion of a neighborhood is extremely large. And just because 2 points, most points are equally far from each other, so a nearest neighbor might not mean anything meaningful. And this could be problematic from a computational point of view as well, but the notion of similarity loses meaning as you go into high dimensions. This applies to all distances. It also applies to Hamming distances. In fact, just like this example that I showed, there's a version of it that involves Hamming distances, same problem. As the dimensionality increases, the notion of a neighborhood becomes problematic. But how do you deal with it? In real life, and thankfully, most data is not uniformly distributed in high dimensions across the entire high dimensional space. So we can try to do some sort of dimensionality reduction to deal with it, or you can try to do feature selection. You can select the best features and try to use only as many features as that are needed. You try out different feature sets and you pick a good set based on a validation set. In one way or another, some sort of prior knowledge is going to help. Okay, I'm going to wrap up. We are a minute over time. Nearest neighbors are perhaps the oldest and the simplest learning algorithm. Prediction may be expensive. There are efficient data structures that can help, like KD trees. You can also use approximate nearest neighbors. Sometimes they tend to be good enough. And this is a well-studied area of research, and it uses tricks from hashing. Nearest neighbors requires us to understand a good distance measure. And you can even try to learn the metric as someone suggested. And this comes under the umbrella of something called metric learning. The hypothesis space of nearest neighbors is the Voronoi diagram. Just be aware of the curse of dimensionality when you're working with nearest neighbors, because you could suffer from it. Okay, we should wrap up. I'm going to stop now. We'll have office hours in 15 minutes, and this will be our last office hours for the semester. If you have any questions, please stop by. Otherwise, I'll see you on Thursday. I'll answer Ola's question. Feel free to leave if you want in the meanwhile. How many dimensions are okay? That's not really, we can't answer that question, because if I tell you 100 dimensions are good, then you could construct a problem where all 101 dimensions are absolutely needed using some sort of parity or something. So it depends on the application. All right, I will see you all on Thursday.